So coming to the decision tree algorithm, it will be said as CART algorithm. So here, it will be said as CART. CART stands for classification and regression tree. So CART stands for classification and regression tree. So here, to get the clear intuition behind this thing, so it means we can use decision tree algorithm for both classification problem as well as regression problem also. That's why it's said as CART algorithm. So coming to remaining algorithms, so there are also few algorithms applicable for both classification problems as well as regression problem. Whereas coming to this algorithm, here it is also applicable for both things. Whereas coming to the difference, so here it is a non-linear and non-continuous. It is a non-linear and non-continuous algorithm. So another words we can say this thing as discrete algorithm. Here it is a non-linear and non-continuous or discrete algorithm. So here, to make you understand this algorithm clearly, I will explain you the intuition of this video by taking simple video. Yeah. So see this video so that you will get the intuition of this thing. So to make a clear intuition behind this algorithm, so I will play the simple video.
Hello and welcome. In this video, we're going to introduce and examine decision trees. So let's get started. What exactly is a decision tree? How do we use them to help us classify? How can I grow my own decision tree? These may be some of the questions that you have in mind from hearing the term decision tree. Hopefully, you'll soon be able to answer these questions and many more by watching this video. Imagine that you're a medical researcher compiling data for a study. You've already collected data about a set of patients, all of whom suffered from the same illness. During their course of treatment, each patient responded to one of two medications. We'll call them drug A and drug B. Part of your job is to build a model to find out which drug might be appropriate for a future patient with the same illness. The feature sets of this data set are age, gender, blood pressure, and cholesterol of our group of patients. And the target is the drug that each patient responded to. It is a sample of binary classifiers, and you can use the training part of the data set to build a decision tree, and then use it to predict the class of an unknown patient. In essence, to come up with a decision on which drug to prescribe to a new patient. Let's see how a decision tree is built for this data set. Decision trees are built by splitting the training set into distinct nodes, where one node contains all of, or most of, one category of the data. If we look at the diagram here, we can see that it's a patient's classifier. So, as mentioned, we want to prescribe a drug to a new patient, but the decision to choose drug A or B will be influenced by the patient's situation. We start with age, which can be young, middle-aged, or senior. If the patient is middle-aged, then we'll definitely go for drug B. On the other hand, if he is a young or a senior patient, we'll need more details to help us determine which drug to prescribe. The additional decision variables can be things such as cholesterol levels, gender, or blood pressure. For example, if the patient is female, then we will recommend drug A. But if the patient is male, then we'll go for drug B. As you can see, decision trees are about testing an attribute and branching the cases based on the result of the test. Each internal node corresponds to a test, and each branch corresponds to a result of the test, and each leaf node assigns a patient to a class. Now the question is, and each branch corresponds to a result of the test, and each.
So here coming to this thing, here whatever the nodes we are keeping at the top, those nodes are called as root nodes. Whatever the node you are keeping at the top, that node is called as a root node. And whatever the nodes you are keeping at the middle place, those are called as branches, or those are called as test nodes. And whatever the nodes returning the output, those nodes are called as leaf nodes or final nodes or end nodes. So here it is a root node here, and these branches are called as test nodes, and these nodes are called as leaf nodes.
Each leaf node assigns a patient to a class. Now the question is, how can we build such a decision tree? Here is the way that a decision tree is built. A decision tree can be constructed by considering the attributes one by one. First, choose an attribute from our data set. Calculate the significance of the attribute in the splitting of the data. In the next video, we will explain how to calculate the significance of an attribute to see if it's an effective attribute or not. Next, split the data based on the value of the best attribute. Then, go to each branch and repeat it for the rest of the attributes. After building this tree, you can use it to predict the class of unknown cases, or, in our case, the proper drug for a new patient based on his or her characteristics. This concludes this video. Thanks for watching. Hello and welcome.
Now we will see the clear intuition of this video.
Hello and welcome. In this video, we'll be covering the process of building decision trees. So let's get started. Consider the drug data set again. The question is, how do we build a decision tree based on that data set? Decision trees are built using recursive partitioning to classify the data. Let's say we have 14 patients in our data set. The algorithm chooses the most predictive feature to split the data on. What is important in making a decision tree is to determine which attribute is the best or more predictive to split data based on the feature. Let's say we pick cholesterol as the first attribute to split data. It will split our data into two branches. As you can see, if the patient has high cholesterol, we cannot say with high confidence that drug B might be suitable for him. Also, if the patient's cholesterol is normal, we still don't have sufficient evidence or information to determine if either drug A or drug B is in fact suitable. It is a sample of bad attribute selection for splitting data. So, let's try another attribute. Again, we have our 14 cases. This time, we pick the sex attribute of patients. It will split our data into two branches, male and female. As you can see, if the patient is female, we can say drug B might be suitable for her with high certainty. But if the patient is male, we don't have sufficient evidence or information to determine if drug A or drug B is suitable. However, it is still a better choice in comparison with the cholesterol attribute because the result in the nodes are more pure. It means nodes that are either mostly drug A or drug B. So, we can say the sex attribute is more significant than cholesterol, or in other words, it's more predictive than the other attributes. Indeed, predictiveness is based on decrease in impurity of nodes. We're looking for the best feature to decrease the impurity of patients in the leaves after splitting them up based on that feature. So, the sex feature is a good candidate in the following case because it almost found the pure patients. Let's go one step further. For the male patient branch, we again test other attributes to split the subtree. We test cholesterol again here. As you can see, it results in even more pure leaves. So we can easily make a decision here. For example, if a patient is male and his cholesterol is high, we can certainly prescribe drug A. But if it is normal, we can prescribe drug B with high confidence. As you might notice, the choice of attribute to split data is very important, and it is all about purity of the leaves after the split. A node in the tree is considered.
So here you need to remember one thing. So here finally we are predicting whether we need to suggest drug A or drug B to the patient. We need to suggest one of these two drugs. So for that purpose, what we are doing? So here we need to choose a best attribute at the root node. Root node is nothing but at the top. To categorize this entire data, we need to consider best attribute. To consider this best attribute, whenever you are using this attribute, it should classify the data correctly. That means here we need to have more predictiveness. That is nothing but, so if you observe this example, here out of all these points, we are categorizing most of the green points correctly, and here we have only one red point. That means here we have only one impure drug. So that is here only we have only one wrong node. So for that purpose, here we are choosing this one as a best attribute. After that, coming to the male category, after going to this male category, here we have 3 red data points and 5 these green data points. So here it is not a pure node. After that, for this male category, to classify this thing further, here I am considering one more feature, that is cholesterol. So based on cholesterol, those who are having high cholesterol, they are taking drug A, and those are having normal cholesterol level on that body, they are consuming green color drug. So that is nothing but drug B. So here whatever the node which is classifying the data perfectly, that is called as pure node. Coming to this node as well as this node, these are called as pure nodes in this scenario. So here pure node is nothing but it is a node which contains only drug A data. It is a node which is containing only drug B data. That's why these are called as pure node. So whereas coming to this thing, it is not a pure node, it is an impure node. So whereas here we have very less impurity. We have only one red point. That's why here I'm saying we are having very less impurity.
Pure if in 100% of the cases the nodes fall into a specific category of the target field. In fact, the method uses recursive partitioning to split the training records into segments by minimizing the impurity at each step. Impurity of nodes is calculated by entropy of data in the node. So, what is entropy? Entropy is the amount of information disorder, or the amount of randomness in the data. The entropy in the node depends on how much random data is in that node and is calculated for each node. In decision trees, we're looking for trees that have the smallest entropy in their nodes. The entropy is used to calculate the homogeneity of the samples in that node. If the samples are completely homogeneous, the entropy is 0, and if the samples are equally divided, It has an entropy of 1. This means if all the data in a
That means sphere nodes contain entropy of 0. And equiprobable node, that is nothing but, so if it is not a 50-50 classifier, so on such cases, we have entropy as 1.
node are either drug A or drug B, then the entropy is 0. But if half of the data are drug A and other half are B, then the entropy is 1. You can easily calculate the entropy of a node using the frequency table of the attribute through the entropy formula, where P is for the proportion or ratio of a category, such as drug A or B. Please remember, though, that you don't have to calculate these, as it's easily calculated by the libraries or packages that you use. As an example, let's calculate the entropy of the dataset before splitting it. We have 9 occurrences of drug B and 5 of drug A. You can embed these numbers into the entropy formula to calculate the impurity of the target attribute before splitting it. In this case, it is 0.94. So, what is entropy after splitting? Now we can test different attributes to find the one with the most predictiveness, which results in 2 more pure branches. Let's first select the cholesterol of the patient and see how the data gets split based on its values. For example, when it is normal, we have 6 for drug B and 2 for drug A. We can calculate the entropy of this node based on the distribution of drug A and B, which is 0.8 in this case. But when cholesterol is high, the data is split into 3 for drug B and 3 for drug A. Calculating its entropy, we can see it would be 1.0. We should go through all the attributes and calculate the entropy after the split, and then choose the best attribute. Okay, let's try another field. Let's choose the sex attribute for the next check. As you can see, when we use the sex attribute to split the data, when its value is female, we have 3 patients that responded to drug B and 4 patients that responded to drug A. The entropy for this node is 0.98, which is not very promising. However, on the other side of the branch, when the value of the sex attribute is male, the result is more pure, with 6 for drug B and only 1 for drug A. The entropy for this group is 0.59. Now, the question is, between the cholesterol and sex attributes, which one is a better choice? Which one is better at the first attribute to divide the dataset into 2 branches? Or, in other words, which attribute results in more pure nodes for our drugs? Or in which tree do we have less entropy after splitting rather than before splitting? The sex attribute with entropy of 0.98 and 0.59, or the cholesterol attribute with entropy of 0.81 and 1.0 in its branches? The answer is the tree with the higher information gain after splitting. So, what is information gain? Information gain is the information that can increase the level of certainty after splitting. It is the entropy of a tree before the split minus the weighted entropy after the split by an attribute. We can think of information gain and entropy as opposites. As entropy, or the amount of randomness, decreases, the information gain, or amount of certainty, increases, and vice versa. So, constructing a decision tree is all about finding attributes that return the highest information gain. Let's see how information gain is calculated for the sex attribute. As mentioned, the information gain is the entropy of the tree before the split minus the weighted entropy after the split. The entropy of the tree before the split is 0.94. The portion of female patients is 7 out of 14, and its entropy is 0.985. Also, the portion of men is 7 out of 14, and the entropy of the male node is 0.592. The result of a square bracket here is the weighted entropy after the split. So, the information gain of the tree, if we use the sex attribute to split the dataset, is 0.151. As you can see, we will consider the entropy over the distribution of samples falling under each leaf node, and we'll take a weighted average of that entropy, weighted by the proportion of samples falling under that leaf. We can calculate the information gain of the tree if we use cholesterol as well. It is 0.48. Now, the question is, which attribute is more suitable? Well, as mentioned, the tree with the higher information gain after the sex attribute. So, we select the sex attribute as the first splitter. Now, what is the next attribute after branching by the sex attribute? As you can guess, we should repeat it. Hello and welcome. In this video, we'll be
So here it is about constructing decision tree. Whenever you want to construct the decision tree, first one is we need to consider regarding entropy. So here, whatever the node having less entropy, we need to consider that node as a root node. After that, we need to consider one more parameter, that is information gain. So whatever the node having more information gain, we need to consider that parameter as a root node. So here, whenever features are categorical, then better to go with this decision tree algorithm. So after that, we have random forest classification as well. Random forest also we can use both classification as well as regression problems. So here we will see the intuition of that random forest. So in the next lecture, we will discuss the programs corresponding to all these algorithms.
Hello and welcome back to the course on machine learning. Today we're talking about random forests. Let's have a look inside. So first thing we're going to learn is a new concept, ensemble learning. What is ensemble learning? Ensemble learning is when you take multiple machine learning algorithms and put them together to create one bigger machine learning algorithm. So that machine learning algorithm, the final one, is actually using or leveraging many different other machine learning algorithms. And they can be the same machine learning algorithm as we'll see today. We're going to be looking at the random forest method, which combines a lot of decision tree methods. So instead of running a decision tree method, which we talked about earlier, instead of running it once, we're going to run it multiple times, and that will give us a random forest. So let's have a look at the step-by-step process to understand how all of this happens. So step one is you pick at random k data points from the training set. Then you build a decision tree associated to those k data points. So instead of building a decision tree based on everything you have in your data set, you build a decision tree just based on some of the data points that you have. So kind of like a subset of all of your data set. Next, you choose the number of trees you want to build and you repeat steps 1 and 2. And then once you have all those.
So here coming to the random forest algorithm. So here we are constructing different number of decision trees. So finally, by constructing different number of decision trees, we are taking average of all the decision trees to get an optimum result. The main goal of random forest is to create more number of decision trees. After creating more number of decision trees, to take average of all the decision trees to obtain the best result. That is the purpose of random forest algorithm. So here, this random forest algorithm belongs to the ensemble family. So here, ensemble stands for, here we are using different algorithms to implement this random forest. So here all those different algorithms are constructed by decision tree only. So to create one random forest algorithm, we are using more than one decision trees. That's why it is said as ensemble method. Random forest is constructed under ensemble method. That is the reason behind that name. So that is random forest.
Trees, you have a new data point. So when you want to check where a new data point falls or how it's classified, for a new data point, you make each one of your entry trees predict the category of which the data point belongs to. And then you assign the new data point to the category that wins the majority vote. So that's how a random forest works. So basically, you start off with one tree and then you build another tree, another tree, another tree. And each one of those trees is being built on a randomly selected subset from your data. And even though each one of those trees might not be ideal, overall, on average, they can perform very well. And that's a major advantage of this algorithm. It's kind of leveraging the power of the crowd, so to speak. Instead of just relying on one tree, it's checking what all the trees are going to say and then just taking the majority vote and deciding the classification based on that. And that power of numbers can help get rid of certain errors and certain uncertainties in your algorithm and make it more precise. And in fact, it's such a good solution that when Microsoft were developing Kinect, this device that allows you to play games on your television, that little device over there, it attaches to an Xbox, and then you can play games without any controller. So here, that device is using an infrared grid to understand where the hands, arms, head, and other parts of the body of these people are located and how they're moving. And it's using machine learning to understand how the body parts are moving and where exactly they're located in space. So when Microsoft was developing Kinect, they decided to go with the random forest algorithm over all of the other machine learning algorithms that were available to them and use the random forest to develop this sophisticated piece of hardware/software. And actually, they have a interesting article about it, so I'm just going to show it to you now. If you can find it on the internet, so it's at Microsoft.com. This is from there, and you can definitely find it there. It's called Real-Time Human Pose Recognition Parts from Single Depth Images. And here it explains exactly, so you can actually see the random forest in action. So you can see that this is similar to what we were talking about before in the classification trees, but here it's actually using random forest to understand where body parts are, and then based on that, the device finds what it needs to do in the computer game. So that's how it works. And so here, if I just search for the word forest, you'll see that decision forest, decision forest, and they actually explain that they were able to achieve faster speeds, faster processing with the decision forest, and therefore that reduced the cost of the hardware that they required for this tool. Interesting article. Check it out if you want to learn a bit more about a real life practical application of a decision forest or a random forest. And that's it for today's tutorial. I hope you enjoyed learning a bit about an ensemble type of machine learning algorithm. Definitely the practical side is going to be quite interesting as well. And I look forward to seeing you next time. Until then.
Great, Ian. So here it is coming to the intuition. Coming to this intuition, if you want a theory, more theory, so I will forward you the material to you after finishing this class. So now madam will forward you the one more link to log in into the session. So here on that session, we will discuss the programs corresponding to the decision tree classifier as well as regression as well as random forest algorithm. Thank you. With this, I am concluding for this session.